We are finally starting the segment of the course that will describe in more detail the major events of Earth history as told by modern scientific research. This video will pick up where the last one left off at the end of the Archean. This time unit is called the Proterozoic, and it spans from 2.5 billion years ago to 541 million years ago. For organization, we divide the Proterozoic into three units: Paleoproterozoic, Mesoproterozoic, and Neoproterozoic. The crust of the Earth was forming ancient continents, and inland seas began to form. By the end, the large continent broke up into smaller ones between 900 and 600 million years. And evidence for glaciers turns up in the rock record. Let's take a look at some of these events and their evidence in more detail. The book introduces an important topic called the Wilson cycle. This cycle involves an ocean basin opening up on top of a continent, sediments building around the rim of the basin, and then tectonic forces that push the continent back together, closing the ocean basin once more. The cycle occurred a couple of times during the Paleoproterozoic along with the Earth's first ice age. Historical geologists identified layered patterns of mudstones that indicate where ice from mountaintops melt to water during the summers and grow during winters. The layer of rock underneath this deposit is intrusive igneous rocks, dated to be 2.6 billion years old, and the mudstone layer has been cut by an igneous rock feature that is 2.1 billion years old. That means that the mudstone must be older than these 2.1 billion year old intrusions, and also younger than the 2.6 billion year old rock beneath it. This relative dating method uses the principle of superposition and cross-cutting relationships to justify an age of 2.6 to 2.1 billion years old for the Earth's first known ice age. You see now why our class spends much time understanding these methods, because it leads to the amazing discoveries of ancient events in deep Earth history. That these events can be understood by science, but lost in time to our own eyes, captures the imagination of geologists and paleontologists alike. If you want to see these rocks for yourself, you must go north to the American Great Lakes. There you can see sedimentary rocks from the earliest inland seas and valuable iron deposits from potentially biological sources that were valuable to modern human civilizations. Well, the iron deposits were at least. Impacts from space rocks and mountain building events brings an end to the Paleoproterozoic era. The end of the beginning, if you will. The Mesoproterozoic era is the unit between 1.6 billion years ago and 1.0 billion years ago. Major rifting, or ripping apart, occurred between the first supercontinent, and it resulted in two smaller supercontinents. Where the rifting occurred, large flows of fluid lava poured out onto the surface, just as it does where tectonic plates are ripping apart today. A mountain building period began while this ripping of the continents was occurring about 1.1 billion years ago. And not much else is known about this event because later geologic events dealt out heavy damage to the rocks of this era. Finally, we come to the last era of the Proterozoic eon, the Neoproterozoic, from about 1.0 billion years ago to 541 million years ago. During this time, a new supercontinent formed at about the Earth's equator, but this continent soon ripped into pieces until about 615 million years ago, when convergence brought them together again. Interesting to note that it is in the middle of the Neoproterozoic that the rocks record the coldest temperatures ever known for planet Earth, it was enough to freeze the entire planet from top to bottom. Evidence for life comes about in the end of the Neoproterozoic at the same time as a warming period that brought Earth out of this extremely cold ice age. Canada is where the extensive rock record is for these events, but the popular Grand Canyon National Park features rocks from the Proterozoic as well. So this brings us to the question of life during the Proterozoic, which is similar to the life forms discussed in the previous lesson video. If we traveled back to the northwest shore of Lake Superior, we might find tiny fossils called microfossils in the Gunflint Shirt deposits. It'd be great to go check that out, but you'd have to get tiny pieces of the deposit underneath a microscope, because that is how small these fossils are. However, they are recognizably photosynthetic and supports the origin of the oxygen in the atmosphere. Another first occurred during the Proterozoic in the history of Earth life, and that is the first eukaryotes. It is important because eukaryotes are the first life forms to not make exact copies of itself during reproduction. This introduced variation into the reproductive cycle, which is crucial for the rapid evolution of the eukaryotic life forms to come in the next eon, the Phanerozoic. Proterozoic life forms were also the first to be made of more than a single cell, also called multicellular, and they are named metazoans. These fossils are researched by only a few brave paleontologists willing to step out of any familiarity with modern organisms and into the Ediacaran period, at the end of the Proterozoic eon. There is much debate about the true nature of these animals, so I'll defer to the PBS Eons video about Precambrian life. And with that marks the end of our time discussing the Precambrian Earth. And that pretty much does it for the lesson. So tune in next time as we continue our march from the past to the present. Thanks for listening.